Hello classmates, welcome back to the class. In this video, we are going to introduce the second time frame expansion method, the 9-value D algorithm, which was proposed by Muth in 1976. At the beginning of this video, please do an exercise. Given this fault and this sequential circuit, run the simulation and see if we can detect this fault by applying a sequence of test patterns 0, 0 and 0, 1. Please now pause the video and try to do this exercise. Okay, have you finished the exercise? If you do it correctly, you will find that the fault-free status of this circuit is 0, 1, and the fault-free output would be 1 in the first cycle and 0 in the second cycle. If this circuit has a stuck at 1 fault, then the faulty output would be 1, 1. Since the output Z is different in the second cycle, we can detect the fault. So the answer would be yes. However, if we try to use the extended D algorithm that we taught in the previous lecture, we would fail. Suppose that we want to propagate this fault to the output. So we apply a 0 to A in the 0 time frame. To propagate the D through this NAND gate, the side input would be 1. To control this side input to 1, we will need a 0 here. If we need a 0 at Y0, we will need a 1 at the NOR gate, which implies that both of the inputs of the NOR gate would be 0. In that case, we will need a 0 at input A in time frame -1. But this is a conflict because this is actually a stuck at 1 fault. So according to the extended D algorithm, this fault cannot be tested. So this is very confusing, since that we already shown that this fault is testable. Why does extended D algorithm fail? This is because that Y0 is actually overspecified in the 5-value logic. If we think about it, actually this value does not have to be 0. This is because traditional 5-value logic can only express 5 different logic states, which is 0/0, which means that the good circuit is 0 and the faulty circuit is 0. 1/1, X/X, 0, 1, and 1, 0. This is not sufficient for sequential circuit. 5-value logic cannot express, for example, 1x, 0x, x0, and x1. So now, here is another quiz for you. For a sequential circuit, how many different logic states do we need to express? Please think about it and pause the video. Have you come up with an answer? For the good circuit and the faulty circuit, we will need 0, 1, unknown. So totally, we will need 3 squared, which is 9 different logic values. So, in 1976, Moore proposed to use 9-value de-algorithm to solve this problem. In traditional 5-value logic, we can only express 10, 01, 00, 11, and XX. Now, in Moore's 9-value logic, we can express 0x, which means the good value is 0 and the faulty value is unknown. We can use the symbol G0 to show this case. And we can also express 1x, x0, and x1. By using Moore's 9-value logic, we can express all the possible logic combinations for sequential ATPG. For example, given a 2-input AND gate, suppose that one of the input is D prime, which means that the good circuit is 0, the faulty circuit is 1. If we want to propagate this D prime to the output, we could have x1, which means the good value is unknown and the faulty value is 1. With this combination, the output can be D prime, so the Fourier effect can be propagated to the AND gate output, even though one of the side input is unknown for the good circuit. Using this 9-value truth table, we can avoid the overspecification problem. The cause is that the truth table is much larger than traditional truth table. As we can see, the size is 9 by 9. Now let's apply the new 9-value logic for test generation. Suppose we want to propagate this 4 to the output Z. The side input would be 1x. Please note that the faulty circuit can be unknown. If this is 1x, then this would be 0x. Then we would need to justify from the left. So this signal would be 1x, which means that the input to A is 0x. This is consistent with the stuck at 1-4, so there is no conflict anymore. Using the 9-value logic, we can now generate a set of test patterns, which is 0, 0 and 1, 0. If we compare the 9-value logic and 5-value logic, we can see the difference. In 5-value logic, we need a 1 here, but actually this is an overspecification. In 9-value logic, we only require 1x. In this case, we can successfully justify this test. In summary, in this video, we have introduced the 9-value D algorithm, which can express all 9 possible logic states to avoid overspecification problem. Before we end this video, we have 2 interesting FFT for you. Question number 1. In the past combinational ATPG, we need only 5-value logic, but now in sequential ATPG, we need 9-value logic. So why didn't we consider these 4 possibilities in combination ATPG? What was the reason? Question number 2. For this specific sequential ATPG problem, we said that we failed to control y0 to 0 because we have a conflict in the time frame. So, can we move on one more time frame to the left? That is, can we control y-1 to 1? Does this work? Please think about these 2 interesting questions. Thank you for watching.